Thank you very much, everybody, for coming today, and for all of you who are watching on our YouTube channel. Today, we have the pleasure of having Dr. Nathalie Oullette come talk to us about the James Webb Space Telescope and hopefully its soon-to-be launch. Dr. Ouellette comes to us as the JWST outreach scientist at l'Université de Montréal. She completed her bachelor's studies at McGill University and pursued a master's and doctoral degree in astrophysics at Queen's University in Kingston, Ontario, under the supervision of Stéphane Cortot. I don't know if you all know him, but he is a truly wonderful guy. After graduation, she became the coordinator for the Institute for Research on Exoplanets, also known as IREX, here at l'Université de Montréal. And as such, and in her role as JWST outreach scientist, she's given dozens of presentations, talks, and media interviews on the role JWST will play in the upcoming decades of astronomy. And I say dozens, but I should probably say hundreds, I'm sure. And today, she will be sharing with us the potential of JWST and how we as graduate students and overall the astronomical community can be involved. So with that, I'm going to stop talking and leave the floor to Nathalie.
Thank you, Carter, and thank you for all of you that are joining live. Thank you for all of you that are watching after the fact. So I want to keep this pretty conversational, honestly. As Carter mentioned, I give a lot of presentations and media interviews, and as such, I talk a lot with the general public. A lot of people who don't know what Webb is, who don't even know that Hubble exists, who don't know what astronomers do, and they think I'm an astrologer, and then they ask me to like give them their horoscope essentially. So I think that there's like lots of room for discussion in this presentation that I'm going to do. I'm going to tell you a lot of broad strokes, but if you want to like pull me in any particular direction, or you want to ask me questions during the talk, I think that's totally appropriate. Feel free to like raise your hand or write it in the chat. I'm able to see if someone writes something in the chat. I'm not like locked inside my full screen presentation or anything. So you can go ahead and interact with me that way. That being said, I've already given 2 presentations on Webb today. They were for elementary school students. I will try to rewire my brain and talk to graduate students. I will talk about some broad general things, but as I said, focus me on certain topics if you're interested. So it's my pleasure to talk to you about the Webb telescope and how we're going to be able to unfold the universe as we never have before. And that is a nice pun, because we're going to need to unfold the telescope before we unfold the universe. So when I give these talks, especially to the general public, I love to talk about how astronomy is the oldest science. That's because you don't really need any tools to do astronomy for the most part. Humans have been able to look and inspect and observe the night sky and see how it changes over time with their naked eye for millennia at this point. But obviously, we have had technological improvements since then. We had the first telescopes pointing towards the sky in the 17th century, Galileo obviously being a huge breakthrough and proponent of that and using tools, and we've had lots of different tools since then. I want to emphasize as a revolution the coming about of Hubble, the Hubble Space Telescope, 31 years ago now. And as we know, this was a project that took many, many years to come about, and we've had the benefit of having this telescope operational for 31 years now. So when it was first launched, some of you may know, or some of you may not know, it wasn't working so well at the very start. There were aberrations in its mirrors. Luckily, we were able to fix it because it's a low Earth orbit, and the Canadarm was actually used to do some of those repairs. And since then, it's been working wonderfully. It's done fantastic science. It's done a lot for the public perception of astronomy as well. The images that it's created has really, really put astronomy on the map, and space telescopes in particular. Obviously, all telescopes are useful, and there are a lot of challenges with space telescopes, but there are certain things you can only do with a space telescope, and I think Hubble was able to really, truly showcase that. One of the things I always like to highlight is the Hubble Ultra Deep Field. I think it really changed the way that we see ourselves within the universe. So if you don't know about it, it is an image that was taken of a mostly empty part of the sky, very, very long exposure, and it allowed us to map out all of these new galaxies we didn't know about. So we're talking tens of thousands of galaxies. And so you can now actually move through this map because we can identify the distance between us and these galaxies. And this really opened up our worldview or cosmo view, and has made us realize that there may be hundreds of billions or even a trillion galaxies in the observable universe. So certain things you need space telescopes to do. And the Hubble Ultra Deep Field is a really good example of that. But obviously, I mentioned this happened over 30 years ago that we put the telescope up. You may have heard that in the last few years, some of the gyroscopes would stop working. There were a few close calls and scares where onboard computers wouldn't be booting up properly. And NASA in general has been very reticent to commit to any further repair missions. And the technology that is on Hubble is getting a little bit older. There have been additional instruments that have been added to Hubble over time, but really we want to be looking forward to a successor for Hubble, and that is the James Webb Space Telescope. We're trying to shorten that a little bit and just say Webb Telescope in general. We call it the successor and not the replacement for Hubble, and that's because we're hoping that both missions will be able to overlap for quite a bit of time. So we wish a long, eternal life to Hubble if it's possible, and that they will be able to work jointly in order to make lots of interesting discoveries. So Webb, like Hubble, is a collaboration between NASA and the European Space Agency, but unlike Hubble, the Canadian Space Agency is involved in Webb, which is really exciting for us. So I'll talk about the Canadian contribution to Webb and some of the really exciting Canadian science that will be going on in the first few years on Webb. And I'm really hoping that this is just the first of many very large space telescope missions that Canada will be involved in further down the line. We've had a lot of success with some smaller missions like Bright and MOST, for example, and we've had some collaborations with other telescopes. But I think that this would be like a really great blueprint going forward with like really other large collaborations, like for example, LUVOIR, which I'll mention at the very end. So why am I talking to you about James Webb? I am the outreach scientist for Canada for this mission. So I work at the University of Montreal, and we have a contract between the university and the Canadian Space Agency. The PI of Webb is a professor at the University of Montreal, René Doyon, and he's the one who sort of conceived of the Canadian instrument. Lots of different people were involved in this Canadian Space Agency, industrial partners such as Honeywell, who was formerly ComDev, and lots of scientists all over Canada and obviously beyond for the international components. So as the outreach scientist, I'm sort of like the bridge between the science team and the general public. So my role is to really communicate any developments with the mission, any great discoveries going on, and a lot of just general astronomy concepts to the public, because the Canadian public funded this with their tax dollars, and so they are allowed to know what those tax dollars went into. So I've had this role since 2018, and I work very, very closely with people at the Canadian Space Agency and at NASA, especially people that work in the communications departments of those two individual places. And by profile, being a PhD astronomer with a communications, not background, but like experience, there are quite a few people like that, especially on the NASA side or the American side, who have that profile. So really, science communication as a career for scientists is really becoming like a viable option for people, which is really exciting. So if you have any questions about getting involved in science communication in general, I'd be happy to answer them. So I have a short video created by the Canadian Space Agency, and it really gives a broad overview of the Canadian contribution to the mission and what Webb will do. If you're interested in finding out more, getting a copy of the video, you can go on this website right here. This is the French website, but you can just like click on the English tab and it'll bring you to the English website. I believe this video is in English though. You can hear? You can't hear? So I might have not selected the like share sound. Yeah, there you go, share sound tab. And then we can just start over again.
That's perfect.
The James Webb Space Telescope is the most powerful space observatory ever built. Gathering infrared light invisible to the human eye, Its penetrating gaze will behold the earliest moments in cosmic time and search distant worlds for evidence of life. The Canadian Space Agency is collaborating with NASA and the European Space Agency on the James Webb Telescope. Canada has contributed two key elements: the NIRISS instrument and the Fine Guidance Sensor. NIRISS will keep watch as faraway planets pass in front of their host stars and will gather the spectrum of light filtering through the atmospheres of rocky super-Earths, mysterious ocean worlds, and gigantic hot Jupiters to create a chemical fingerprint that could be a match with the vital clues of life. Water, carbon dioxide, and oxygen may lurk within the atmospheres of these enigmatic exoplanets. NIRISS will also take a closer look at the distant universe, peering back in time to see youthful galaxies just cosmic minutes after they form. To perform these unprecedented observations, sometimes from billions of light years away, the telescope's gaze must stay perfectly still. Webb's Fine Guidance Sensor will latch onto key reference points in deep space during all of the telescope's observations. Its remarkable precision will help the telescope capture sharp images of swirling, merging galaxies, newborn stars, and bubbling nebulas that have never been seen before. The James Webb Space Telescope will pierce through layers of cosmic dust to unveil the unique mysteries of the universe and fuel groundbreaking astronomical research for decades to come.
So there was a lot of information in there, a lot of broad topics. I'll delve into some of those topics, but at the very end, and there's a reason why we end on this, this telescope is going to generate huge amounts of data that will be put into your hands, graduate students, really. So you will be able to really exploit these data and make fantastic discoveries in the first few years of Webb. So that's super, super exciting. So a little bit about the mission first before we delve into the science of it. So some of you might be familiar with the fact that the launch of this mission has been delayed numerous times to the point where it's almost become a bit of a joke. But the essence of the matter is that we had a second shot with Hubble. When it was sent up, there were problems and with the mirror, and the images that it took firsthand were not great, but luckily we could send someone up to fix it because it was in low Earth orbit. Because of the orbit where we're sending Webb, and I'll mention that a little bit later, we cannot fix it if there's anything that goes wrong. And there are a lot of complications related to the size of this telescope that makes it a very complex instrument to deploy in space. So it needed to undergo very, very rigorous testing. So this is an image of the telescope's mirror about to be put into a vacuum chamber to simulate the vacuum of space and make sure that all of the components hold up to the environment of space. Another example is we have to shake this thing up really violently to make sure that it can withstand the environment of a rocket launch. So here you can see that it's on a vibrating platform for vibrational and acoustic testing to make sure that when we strap it to a rocket and launch it into space, it's not going to just fall apart. And these tests were performed on each instrument and piece individually, and then the pieces were assembled together. And then it was again, these tests were again performed on the pieces put together. So there were like very complicated and many steps in order to do all of these tests very, very rigorously. So if we ever hit a test and the results are not optimal or what we were expecting, it is best for us to delay the launch and re-perform the test and solve the issues when the telescope is here on Earth and it is easily repairable and accessible. So these were very, very important tests going on. But finally, these tests were completed over the summer. They had been going on for many years, obviously, but then the telescope was stowed into its stowed configuration and ready to be shipped. So here it's all packed up, and this is essentially what it will look like inside of the rocket that launches it. And it went on a long journey over several weeks to go to its intermediate destination, the Guyana Space Center in Kourou. So its last testing site was at Northrop Grumman in Redondo Beach in California, right here. It was put into a boat, on a boat, and it went on a long journey. It had to go through the Panama Canal and then eventually land in Kourou, where it is currently being prepped for launch. So this was actually a very top secret enterprise because we had some concerns that pirates, real like modern day pirates, might like intercept the ship. It is a $10 billion machine. So, you know, imagine the ransom note for that. So this was like cloaked in a lot of secrecy, but once it was finally safely arrived at Kourou, we were able to announce it. So it arrived October 12th on site. And there it's going to be put on an Ariane 5 rocket, as you can see here, to its final destination, space, and specifically a Lagrange point called L2. So this is a picture of it arrived here in a spaceport. You can see it's like in a little container and everything. And now it's being prepped for launch. There was an intermediate step that needed to happen before it could really start being prepped. And that was a launch of another Ariane 5 rocket. It was supposed to take place on October 22nd. It was only delayed one day, so that's good news. October 23rd, it was a payload of some communications and military satellites from Europe. And there weren't any problems with that. So that's a really, really good piece of news. And now the next launch that's scheduled for Ariane 5 is James Webb. So that's super, super exciting. So this is a diagram here of what the telescope will look like in its stowed configuration inside the rocket. So you can see it at the tip here, and this is a very big telescope, and you'll get a sense of how big it is. Ariane 5 is actually one of the biggest rockets that we have, but even in this big rocket, you need to sort of fold it up. The video that I typically show to give a sense of how complicated this deployment sequence is this one. And so you can see that while it's deploying, it's moving to its final destination. But instead of showing you this one, there's actually a new video, and it's a little bit long, but bear with me because it is the one video that has, I think, can best communicate the excitement, but also sheer anxiety that the entire Webb team is feeling right now, knowing we're strapping a $10 billion machine to a rocket and like praying to God that it deploys in space. So hopefully this makes you feel the sort of like anxiety and excitement that we're all feeling too.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time, almost 14 billion years, to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space. 6, 5, 4.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, or approximately 8,900 square feet, almost the size of 3 tennis courts, of very thin Kapton material, about 1 to 2/1000ths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy aside. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
All right. I don't know how you feel about seeing that, but every time I watch that video, I'm like filled with awe and dread, and I feel goosebumps and all kinds of emotions. So I think it's a really fantastic video. It was only released about a week ago, and I'm trying to show it to as many people because NASA did, I think, a fantastic job to really communicate the complexity of this mission. So a few notes about the comparison that many people do between Hubble and Webb. You might know that Hubble is a visible optical telescope, so it's looking mostly in the same kinds of light that are visible to us. There's a little bit of UV and a little bit of near infrared as well, whereas Webb will be really concentrated on infrared light, which is why its mirror is conceived the way that it is. So it's quite a bit of a larger mirror, 6.5 meters wide compared to Hubble's 2.4. It's a segmented mirror, and as mentioned in the video, each mirror will have actuators to really focus it and make it really take clear images of its targets. Instead of being coated in aluminum, the segments are coated in beryllium and gold. It's made of beryllium because it's a lighter kind of glass-like material, and gold because gold is very, very highly reflective for infrared light. It is also a mirror that is built not within a tube, but out in the open, because if it is in a tube, we can have a tendency to trap heat within that tube, which would cause sort of like light pollution in the infrared. So it's a very distinctive configuration for the telescope, but might be used moving forward for larger telescopes like LUVOIR, for example. We mentioned the sun shield, which is a really essential piece of the observatory. The telescope will always be placed such that the sun shield will be between the sun and Webb itself. So to compare the temperatures between one side and the other, on the hot side, we're talking about 85 degrees Celsius. That's where you have the solar panels, the communications antenna, so it will always be pointed back towards the Earth. There will be no downtime in that sense. And in the cold side, you have the mirror itself and all of the scientific instruments, and that is cooled down passively, meaning that there is no mechanism other than just shielding that part from the sun. It's going to be cooled down to about 40 degrees above zero, so minus 233 degrees Celsius. However, there is one specific instrument called MIRI that will be looking at the mid-infrared that needs to be actively cooled further. And so it has that radiator, like a little refrigerator that cools at several tens of degrees colder than the other instruments in order to observe in the mid-infrared. So we talk about how we have no second chance with Webb, and that's because of its location. So it's going to be in orbit around L2. We sometimes simplify and say it's going to be at L2, but it will actually be on a very large orbit, larger than the orbit of the moon even, around the Lagrange point L2 in the Earth-Sun system. So this means that it has the same orbital period around the sun than the Earth. It's always placed directly behind the Earth. And it doesn't need a lot of propellant to stay there. Lagrange point is a quasi-stable Lagrange point L2. And so the propellant needed to keep it in the orbit around L2 is minimal. You still need a little bit. So the propellant is still the limiter for the mission lifetime, but there's not that much propellant that's needed to keep it there, which is good news to try to extend the lifetime. So this is the orbit here. Infrared light. So you have here the electromagnetic spectrum. You can see a few other key telescopes and where they lie on the spectrum. Hubble, mostly in the visible, a little bit in the UV and near infrared, as I mentioned. Spitzer overlaps a little bit with James Webb. However, Spitzer had a much smaller mirror, as you know. And if you're thinking of Herschel, Herschel was in the mid and far infrared, so it doesn't have an overlap so much with Webb's windows. And infrared astronomy is very important. It's often not as glamorous, perhaps, as visible astronomy, but there's lots of stuff to be done there. Planets are very bright in the infrared. This is a picture taken by Juno with an infrared camera of the North Pole of Jupiter. Protoplanetary disks, exoplanets, many types of cooler, colder, less massive stars shine very brightly in the infrared, and they are the stars that are the most common in the initial mass function, as you might know. If we're interested in looking at very distant early galaxies, we need to look at the infrared. So these galaxies, when they were formed, were very massive, very, very active, and very bright in the ultraviolet and blue light. However, because of redshift, by the time they get to us, they're actually in the infrared light. So we need an infrared telescope to be able to study these very early galaxies. Another reason why it's very important to look at infrared, you can pierce the cosmic veil of all of this dust that's in these nebula. And here is a great example, these pillars of creation. You can actually see the massive sea of colder red dwarf stars that are much brighter in the infrared versus in the visible. So you're really opening up a new window into the universe by looking at the infrared. So there are 4 scientific instruments on Webb. One is a dual instrument, which is the kind of contribution from Canada, and I'll talk specifically about that in a moment. So this is the electromagnetic spectrum. You can see that most of the instruments are in the near infrared. So FGS nearest is the dual instrument from Canada. Near spec and near cam, one is a spectrograph, one is an imager, and they're really in the near infrared. And each has specific teams and specific scientific missions. And you have MIRI, which is the mid-infrared instrument, which will be actively cooled on top of being passively cooled in order to be able to look at this part of the spectrum. So all of these instruments are combinations of cameras, spectrographs, or coronagraphs. So you can see in this little diagram here, near spec, obviously a spectrograph. Near cam will have some spectroscopic components, but its main use is imaging with a coronagraph. MIRI is going to have components of all these different sections, and you're going to have components of all these different sections as well in the FGS nearest Canadian instrument. So the Canadian contribution that we're very, very excited about, it's a dual instrument about the size of a washing machine. One FGS is mission critical. So this is a fine guidance sensor that will allow the telescope to point and remain stable on any target. It's going to be using the same target catalog as Hubble for its pointing guides. And basically, anytime you see an image taken by Webb, regardless of the scientific instrument that took the image, FGS comes into play into all of those observations. So this is a mission critical piece, and it is probably the most sensitive fine guidance sensor that's ever been put on a space telescope. The rough estimate that we try to give to indicate its sensitivity, it can discern a human hair from about 3 or 4 kilometers away. So that's how precise its pointing is. NIRIS, or the Near Infrared Imager and Slitless Spectrograph, is the scientific instrument component of Canada's contribution, and it's going to have many different things that it can do. Its imaging is mostly really in conjunction to its spectroscopy work, working sort of as an IFU. It's also going to have some great interferometry components to it. It's going to be able to take some images, direct images of protoplanetary disks, of exoplanets, as well. So there are different modes that are specific for different kinds of targets. The PI of this is René Doyon, who is a professor at the University of Montreal, and he's also the director of the Institute for Research on Exoplanets. So it's no wonder that NIRIS was designed in great part to study exoplanets and specifically studying the chemical composition of exoplanet atmospheres, potentially finding signs of habitability or maybe biosignatures. We don't want to oversell the capacities, but we can at least start answering the beginnings of those questions a little bit more. So in exchange for this great Canadian contribution, Canadians will be able to gain access to at least 5% of Webb's time during its operations. Some of that time is divided between different programs. So one of the programs is called Guaranteed Time Observations, and this is in direct trade with the contribution from Canada. So these are 450 hours that have already been delegated to a number of projects, 2 of them being really huge projects. They're both 200 hours long, thereabouts. One is on exoplanets, one is on distant galaxies, and I'll mention them briefly in a few moments. On top of that, you have, of course, the General Observations Program, which is just the competitive telescope time proposal process. And so about a year ago was the deadline for all of the cycle 1 or the year 1 proposals for Webb. And the winners, or the allocated time, was announced earlier in the spring. And so in Canada, we had 14 proposals for a total of 331 hours that were retained. And these are proposals led by Canadian astronomers, so PI or co-PI. We have 72 more that have Canadian collaborators on it as well. There was an oversubscription of about 4 to 1 for this, and that's not as big as you might expect, but the proposal process for Webb is a little bit more involved than on other telescopes. If you're familiar with how to apply for telescope time on proposals, there's like a phase 1 and a phase 2. Phase 2 is sort of like melded into phase 1 for Webb, and a lot of these instruments are new. A lot of these different modes people aren't so familiar with, and a lot of people are waiting to see how it goes for cycle 1 before applying. So we're very encouraged by these numbers, and we're hoping more people will apply for cycle 2 as well. There's also a special program called Early Release Science, and this was a competitive process where people were trying to gain very, very early access to the telescope, with a promise that the data they would take would benefit a large number of astronomers. They would make it publicly available, train astronomers to analyze this data and use it. So one of these ERS programs, co-led by a Canadian, was retained, and I'll mention what it will be studying in a moment. So there are different scientific missions for Webb, the first being what we call alien worlds. So I mentioned already the capacity of NIRISS for studying exoplanet atmospheres. So as you may know, one of the ways that you can figure out that an exoplanet exists is by looking at transits of these exoplanets over their stars. So looking at periodic dips of their luminosity. But what blocks out the light of a star is the opaque part of the planet, or the rocky part of the planet. In the instance of certain planets, be they rocky with an atmosphere or gas planets, you have a part of the disk that is actually transparent to starlight. So what happens there is when the exoplanet transits over the star, some of the starlight will stream through the atmosphere of the exoplanet, and some of the starlight will be absorbed by some of the chemicals inside of the atmosphere of the exoplanet. So it will leave an imprint, the atmosphere will leave an imprint in the starlight, and you'll be able to determine certain chemical components of these different exoplanet atmospheres. So you can get a spectrum and see signatures of oxygen, carbon dioxide, methane, ozone, and different ratios and combinations of these chemicals can indicate the sign of biological activity or life. So there are many interesting targets, and one that I can mention is TRAPPIST-1. It's a 7-planet exoplanetary system, 3 or 4 of the planets being in the habitable zone. Very interesting in terms of trying to find signs of life. And we actually have a really exciting program to study many TRAPPIST-1 planets, led by Olivia Lim, who is a PhD student at the University of Montreal. So when we talk about finding alien life here, and this is more for like the general public, we don't necessarily mean like little green men. It might be something very simple like a bacteria or a microbe, but it would still be very exciting and a huge step in answering, are we alone in the universe? We also have interesting targets within our own solar system. I can mention Enceladus, for example. This is an image of cryovolcanoes on Enceladus. There have already been some preliminary studies done by Cassini, for example, as it was orbiting around Saturn. And in a similar way that Webb will be able to look at transit spectroscopy for exoplanets. It will be able to look at the chemical composition of water coming out of these cryovolcanoes and potentially finding signs of habitability or maybe biosignatures within these ejections that are coming from the underwater or underground liquid ocean on these water worlds. So in terms of Canadian science for planets and exoplanets, we have one of the two GTO programs that I mentioned called NEAT, and it is a study led by David Lafrenière, who is at the University of Montreal, to use NIRISS in its single object slitless spectroscopy mode to study the atmospheres of exoplanets. So 204 hours will be dedicated to this in the first year of Webb, so very exciting. There are 5 GTO programs that have been retained, and a lot of them are being led by PhD students, graduate students, which is super exciting because in the Cycle 1 telescope time proposal process, it's double blind. No one can see who actually submitted. So I think that took away a lot of the bias. And so a lot of graduate students are gaining really great time on Webb because of that. So 5 GTO programs on rogue planets, brown dwarfs, protoplanetary disks, and exoplanets as well. We also have some GEO programs on trans-Neptunian objects inside of our own solar system. So very exciting. Another big scientific goal of Webb is to study the stellar life cycle. So that goes from the formation of solar systems. And for this, one mode on NIRISS will be very important. It's called AMI, aperture masking interferometry. So it's the coronagraph component of NIRISS. It's going to be able to, we hope, block out central stars and image these protoplanetary disks and stars being formed, solar systems being formed. We're interested in the entire gamut of the stellar life cycle. Things that are maybe not quite stars like brown dwarfs, stars that are being formed in photodissociative regions. So this is a nebula where very, very massive stars are injecting loads of energy into their environment and chemically changing their environment. And all the way up to the end of the stellar life cycle concerning black holes. So for Canadian science with stars, there's the ERS program, or Early Release Science program, that I mentioned, led by Els Peters at Western University. And she's going to be studying those photodissociative regions in the Orion Nebula, where massive stars are injecting loads and loads of energy inside of these nebula. We also have GEO programs, 3 of them for a total of 53 hours on kilonova explosions, led by Maria Droud in Toronto, where she's going to be studying the formation of very heavy elements caused by neutron star collisions. There's a program by Harvey Richer at UBC on white dwarfs, and there's a program by Eric Brozolowski at the University of Alberta on star formation inside of galactic spiral disk arms. Another big component, including using NIRISS, is studying galaxies through time. So we want to study how galaxies evolve over the course of the entire history of the universe, from the very first galaxies through massive galaxy assembly, all the way to the current day evolution. And one of the key parts that helps with Webb is the imaging, the resolution of the imaging that's going to be happening. So this is an image here of what a galaxy would look like taken by Hubble, and a simulation of what it would look like taken by Webb. So already here, you can see star formation knots throughout the disk that are not visible with the resolution of Hubble. So you're improving your resolution with Webb quite a bit to look at these different components of galaxy evolution. We'll also be using gravitational lensing as a little trick to try to gain access to those really, really far away galaxies. So that's going to be one component important in one of the Canadian programs called Canucks, to study cluster galaxies that are very, very far away. It's a very nice name, yes, I know. Obviously, one of the challenges is you're going to have to, these gravitationally lensed distant galaxies are deformed, so we need to think of machine learning and computer algorithms to reform what these galaxies look like, but at least their spectra will remain basically unchanged, other than redshift, of course, and you'll be able to study star formation and mass and other key components of these faraway galaxies. So in terms of Canadian science for galaxies, there's the GGO program Canucks that I mentioned, 199 hours, led by Chris Willett at NRC Herzberg. And they're going to be using NIRISS, the Canadian instrument, in the wide field slitless spectroscopy mode. So looking at many different objects in one single image using gravitational lensing, as I mentioned. There's another GTO program for 5 hours looking at high resolution imaging of galaxies using the AMI mode, the interferometry mode. And there are 4 GEO programs for a total of 78 hours on galaxy formation and evolution and supermassive black holes and their effect on galaxy evolution. And then the final big piece in the scientific missions for Webb is studying the early universe. So Hubble was able to push the limit to about 500 million years after the Big Bang. With Webb, we're hoping to push it 200 million years after the Big Bang. Now, often when I tell this to the public, they like, it doesn't sound like that big of an improvement, and it sounds like 200 million years is a long time, like when we're looking at human history. But if you put the entire history of the universe, 13.6 billion years, on a calendar year, and we put current time at like midnight on December 31st, looking back 200 million years after the Big Bang is like looking back at January 6th earlier this year. So you're looking like really far back at like some of the very first galaxies that have ever been formed. So just to conclude, beyond Webb, I'm really hoping that the success of Webb is going to incentivize the Canadian Space Agency, the Canadian government, any kind of budget stakeholders to encourage Canadian participation in future missions. So the next big mission on the docket in terms of space telescope is the Nancy Grace Roman Space Telescope, formerly WFIRST, which will have key components in better understanding dark energy, taking observations of exoplanets using coronagraphy, among other things. And the window is closing for Canadian participation on this, but maybe through Canadian industry and some of the cameras and detectors on the telescope, there might still be hope. But this will probably be launched in the next 5 years or so. And I think that Astro 2020 is finally supposed to come out on the US side, where they can start giving recommendations on the next big space telescope that's going to sort of be the successor for Webb. LUVOIR is a fan favorite. This is a comparison of the size of LUVOIR and the Hubble Space Telescope. So this is Hubble here. And as we zoom out, you're going to see the sheer size that's proposed for this telescope, which would look in the ultraviolet, optical, and infrared, with a style, a configuration quite similar to Webb. We're thinking of a mirror between 9 and 12 meters wide. So like truly gigantic. There's different things on the table. Potentially it could be partially constructed or assembled in space. Any big space telescope moving forward, we would want to be refuelable, repairable, sustainable, unlike Webb, which won't be repairable. So these are some of the big pieces that are coming up in space astronomy after Webb. And of course, I'll mention really quickly CASTOR. I know Pat Cote gave a talk on CASTOR. I'm very excited about this potential mission. It would be basically a Canadian Hubble looking at ultraviolet and blue light. And not only would it be great for just Canadian participation in a space telescope mission, but it would show that we can take the leadership on one of these space missions. And I think that this would be really fantastic. And as this is something on the order of the next decade, it would be really great for graduate students to get involved in this specifically, as you might be the next leaders for these space telescopes. So if you're interested in getting involved, of course, I encourage you to write proposals for Cycle 2 on Webb. Contact us if you're interested in finding out more on how to use the different instruments. We have lots of resources in-house, or we can refer you to people at Space Telescope Science Institute. But one thing I want to mention, especially today, as I'm the outreach scientist, is there's lots of different opportunities for you to get involved with outreach. With Webb. So one of the things coming up is the launch, which is planned for December 18th. And then there's a 6-month period for commissioning, the release of the first images. And we're getting lots of requests and interest from science centers, classrooms, the media, lots of different places who want to throw events, show presentations, have interviews with astronomers. So if you're interested in becoming an ambassador for Webb and being connected to these different people and stakeholders and publics, you can just sign up to this Google form right here. So it's bit.ly/CA_Webb ambassadors. It's going to ask you where you're located, what kind of outreach you're interested in doing, how you're involved in the mission if you are. And it's not a blood contract, it's just a show of interest. We're building a catalog of people that might be interested in doing outreach. But we'd love to have graduate students involved as well, because you would be great ambassadors for this mission. I encourage you to visit our websites if you want to find out more. So this is the UDM James Webb website, or you also have the Canadian Space Agency one. And you can always contact me if you need any help. I can refer you to other people, but we have an outreach help desk for Webb, essentially. If you want to do an interview with like CBC, you're getting a request and you don't know how to like do an interview, I can coach you through it. I can give you tips and advice. It would be my pleasure. And I really hope that you're excited for this mission and that you might consider getting involved. So thank you.
Thank you very much, Nathalie, for that wonderful discussion about Webb. I had a long list of questions that I wanted to ask you, and I ticked every single one of them off during this presentation. So
good.
Thank you very much for that. I'll also say, take Nathalie up on her offer to help you with media presentations. She is a fantastic media personality. Her interviews are always extremely interesting and very well performed. So
thank you.
Thank you once again, Nathalie. So I want to open it up to anybody. If anybody has any questions that they would like to ask Nathalie, or anything they would like to be clarified. I'll start with Blake. I see you have your hand up.
Yeah, thanks so much, Carter. Thanks so much, Nathalie. That was super interesting. I was particularly interested in the sheer amount of like publicity that has been made for Webb. I recognize that it's a very pricey telescope, and like, so we have to communicate that to the public. So all of those videos you were showing of like explaining the telescope, how it's going to work, I was quite interested in like the process of creating those types of resources. And if there were many grad students, for example, that were involved in the production of those resources. And if for like telescopes in the future, like future Canadian involvement, if that would be like an angle that could have more grad students involved, because I can think of like, even if they're not scientists, if they're like media grad students, for example, they would be able to be involved in a project like this.
Yeah, that's a really interesting question. So yeah, there's like lots of really well-made media products and infographics and everything. NASA, obviously, they have the budget and the means, so they create a lot of stuff. But even at the Canadian Space Agency, we've had quite a bit. Typically, what ends up happening is you'll have a team of professional communications people putting together ideas and scripts and storyboards, and having people like me who are communications minded but have the scientific background vetting all the science behind it. So they'll like write an initial draft of like a script or something, and then they'll pass it through different scientists who could be like, no, that's not quite right, or like, oh yeah, that's a good way to explain it and everything. In other cases, for example, the Canadian Space Agency's website, most of the material on Webb was created by me, so you can end up being like on contract for that. I don't know of a lot of graduate students who are in astronomy who get involved, because typically they are so like concentrated on their thesis work that ends up sort of like invading their entire life. But I know that there are interns, like communications and journalism interns, at places like the Canadian Space Agency or NASA or Space Telescope Science Institute that can get involved in that. And personally, I like to think that there's room for science communication in a graduate student's toolkit. And I'm hoping that we can integrate more students in that. I know for Castor, this is something that we really would love to do. We need help. I'm sort of like the main person in charge of Castor outreach, but like I sort of have this other telescope that's like keeping me occupied right now. So having graduate students giving us a hand for Castor outreach is something that we would really love. So I think that moving forward, it's something we want to move towards.
Thank you so much. That's always great responses. So thank you.
All right. Thank you very much again, Nathalie. I don't see any other questions right now, and we're at the top of the hour, so this seems to have been timed perfectly. I just want to thank you once again for coming in this really wonderful presentation. We are looking forward to the December 18th launch of JWST. I will be watching it, biting my nails. I know Professor Doyon will be terrified for the following 2 weeks.
Yeah, he will be in Kourou at the launch site. So
wonderful. So thank you once again. And with that, this will end our session of CaTS today. So thank you.
All right, thank you.